Welcome to Scaling Pinterest. My name is Marty, and my other speaker is Yash. And today we wanted to take you through a tour of what it was like to build Pinterest from a couple thousand page views per month to billions. And in particular, we want to give the talk that we wanted to be, that we would have liked to have attended last year when we were a tiny company, growing like crazy, a lot of options on the table, and not some clear guidance on where we should go or what options to choose for our infrastructure. There's a lot of choices out there. There's hundreds of them. 20 to 30 are actually good, and 2 to 3 are actually very good. So what we're going to do is I'll describe what Pinterest is, I'll describe a little bit about how we grew and what that felt like and what that looks like, and then we'd also like to talk about what worked, what didn't work, and the lessons that we learned along the way. So first, for people who don't know, Pinterest is it's an online pin board to organize the things that inspire you. So you go around to the internet, you find things that you like, little images, all these great little tidbits, and you bring them back and you put them on boards and you fill out, you curate a bunch of the things that you like around the world. And then also all of those link back to the original source. Like every social networking site, we have users. This is me. A user is links back, they have authentication, they have a description of who they are. On Pinterest we have boards. Boards are collections of pins, and pins are individual images. For instance, here's one pin. A pin, and you can think of it as an image that someone really liked, and there's some extra information around it. So there's a description of why it's important to them. There's a little bit of information, meta information, who owns the pin, these sort of things, who's allowed to see it. And then there's, very importantly, there's where it came from. In this case, I uploaded it. It actually, I didn't source it right. If I linked it from I Can't Hash Cheeseburger, then it would have had a link back to them. And that's very important. So if somebody pins something from Etsy, it will link back directly to that product on Etsy. Also, just like any other social networking site, we have the ability to follow people that you like. You can follow users, you can follow boards, and when they pin something, when somebody I'm following pins something, it goes into my feed. And so here you see a list of the pins that of people I've followed. And so to get your head into engineering mode, I'll show you what our basic hierarchy of our core data set looks like. We have users, users have boards, boards have pins, and then also, shoot. Users can follow other users, users can follow other boards. This is our core hierarchy. We also have other little bits here and there, like a user can like a pin, or a user can repin other people's pins, that sort of thing. So to give you an idea of our growth, I had to leave off numbers here, but you can think of the top scale as being, it's page views, and you can think of the top bar there being bajillions. Billions is the number I'm allowed to quote. And just like any other company, I want to give you a tour of how this grew. It started in March 2010 was really when it started to be released, and we're small at the time. We have a design and we had a schema, so that the product is still being worked out, and we don't even know what the infrastructure looks like. So we're working out the product. We need to keep the infrastructure very elastic so we can change it however we want really fast. So we were on Rackspace. We had one small web engine running Python and one small MySQL database to store the data. Then for the next about 8 months or so, we were what our founder describes as, we were in stealth mode, but we didn't want to be. You know, nobody knew about us. But we were starting to pick up some traction. We were past family and friends. We're growing just a little bit, and now we're to the point where our infrastructure is a little bit more complicated. The design and product were really actually kind of solid at this point. They haven't changed much since then, so that was good. So our infrastructure was really the next big piece to tackle. At the time, it was fairly simple. It was we were on Amazon. We had S3 for our images. We don't host any of our own images, any of the pinned images, and we had CloudFront fronting it. We had an engine of Xbox with 4 web engines, also still running Python. We've always run Python. We had one MySQL database and one read slave for backup mostly, and we had task processors, MongoDB, and a few other boxes here and there. So it was nice and simple, but you'll notice there's no cache on here, there's nothing. Finally, at this point, some of our really bad SQL queries, our massive joins and our distincts and all of our other weird constraints are starting to show their scalability bottlenecks. And we were starting to grow like mad. We started being picked up. So fast forward to September, and we've just been through a wild ride. It doesn't matter what scale you're at, it's really about the growth. And the whole way up, we were doubling every month and a half. And so every week, something new was broken. And it was just a massive, massive pain. And when you're in that mode and you're not getting any sleep, you're constantly trying to find a solution that will just take care of it for you, it'll solve it all for you. And you don't want to do, you try to avoid certain engineering things because you're working on others. And what would be great is if there was a magic clustering solution that scaled for you, and you didn't have to have a schema, and you didn't have to, you add boxes, you hit the button, boom, it's available. And, when that happens, and when you see all these promises, you do what we do, and that's to become a mess. We had, at some point, we had Cassandra, Membase, Memcache, Redis, Elasticsearch, Mongo, MySQL, and a few others floating around in there. And what happens at that point, at this point we had 3 engineers. It was 2 engineers and one other guy who just come on. So it was really 2 engineers scaling up all of this stuff, and we had to be experts in all of these pieces. So we had to know when they fail, how did they fail? Cassandra fails in a very different way from Membase. And knowing all those pieces or having expensive support contracts, it's too much. And at this point we were also on the edge. So every one of these services was hot. It was grinding to a halt. So we decided it was time to do some big drastic changes. This is the point where we split out our whole database, re-architected everything, and we simplified. We learned our first lesson here, and that was, if you bring it into your system, it will fail. So when it fails, you have to be prepared. So keep it simple, just have a few in there. So our architecture changed drastically, and now fast forward to where we're around. Now, this graph is from about February, and now we're back to a simple layout. We have MySQL and Redis and Memcache at the core of it all. Much easier to manage, much simpler, doesn't fail in many complicated ways, and life is good. I'd like to tell you about why some things survived and why certain things, other things did not, because we were surprised by some of them, and I thought that'd be interesting to relay this. So why Amazon? A lot of people ask us this, some because they're amazed that we can stay on Amazon all the way through. And Amazon has very good reliability. I've been in data centers and I've been in Amazon, and I still feel like the reliability is still very good. It's got great reporting, great support, great tools. So if you're growing a company and you don't really want to write your own load balancer, bring in all these tools, they've got it for you. They've got DNS, they've got MapReduce. So we actually use load balancing, DNS, and MapReduce now. It's great. We don't have to set it up, it just works. They also have databases. We don't use them, but they look great. They manage the database, and they'll grow with you. They have basically Memcache that they manage. So you say, I need this many gigs. You don't have to manage individual Memcache boxes. So it gives you a lot of flexibility to grow with you. The best part about Amazon, the thing that we cannot beat as we were growing so rapidly, is that you can have new instances up in a second. I mean, like 5 minutes, and if it takes longer than that, I'm surprised. It never takes more than 5 minutes. And combine that with Puppet or some other automated imaging system, you have a new box ready in 10 to 20 minutes, depending on what it does. So if we're scaling one day, oh my God, we need another cache, we need it now. We can have 10 caches up in 20 minutes and in our pool ready to go. What are the cons of Amazon? Limited choice. So our database boxes, all of our database boxes are a 4-way rated, simple hard drives, low-speed hard drives with 15 gigs of RAM. So it's not too big. If we wanted to have the big, 256 gigs of RAM on top of SSD, we can't. It's the nature of the beast. We can't have it. But what is the pro? Limited choice. We don't have to go out to Dell and figure out, do we want a 3 gigahertz, 3.3 gigahertz, agonize over it. It really just, it simplifies the whole process. It also drives our architecture. Our whole architecture is around working on simple commodity hardware. So now we can take this and go anywhere. We didn't go the route of being able to say, we've got a bad joint, let's throw an SSD at it, and we'll survive for the next 6 to 12 months. We actually we were forced to engineer it, and that was the right thing to do. Engineer it right when you're young. Why MySQL? MySQL is extremely mature. It's been around for 27 years. It's extremely well known, extremely well liked. Everybody who you talk to, if you're hiring an engineer for web, they've either heard of it, or they've admined it, or hell, they may have even written part of it. It rarely has catastrophic loss of data, or any loss of data. We've never lost data on it once that I can think of. Response time to request rate is almost perfectly linear as far as I can tell. As you bring in the request rate, some machines, some different clustering systems, as the request rate gets high, your response time will suddenly shoot up. We had one shoot up over the course of 6 hours, went from 10 milliseconds to 10 seconds. This is one random clustering solution. I'll just leave the name. MySQL will perfectly go until you decide, look, 3 seconds is too much for this particular box, or 100 milliseconds, whatever your SLA is. That's one of the reasons I love it. Very good support. You've got extra backup, which allows us, from Percona, that allows us to do online backups and then recover instantly. We don't talk about anymore about recovery taking days or a week. You have InnoTops, you can introspect on what's going on right now, and MapKit's great for profiling. The community is awesome. Everybody talks about MySQL. The MySQL dev site alone is fantastic, and there's other sites that people just love to talk about it. And you can go on Google and find your fix for any problem you have in a second. And also, there's very good support from Percona if you need someone to come and look at it. And you don't have that with certain other systems out there that are open source and free. And also, MySQL is free, and I love free. In general, actually, I'll just say this about our infrastructure. Free was something that we sort of stood by. I mean, we could have gone out and immediately thrown a lot of money at IBM or somebody, but at a web company that's a startup and not much money and trying to stay lean, you just can't do it. So why Memcache? Memcache is also extremely mature, very good performance, well-known, well-liked. It never crashes except when the box goes down. So if Memcache can solve that, that's a bigger thing. Very few failure modes. This is extremely important. I think the only way I know that Memcache fails for us is if you give it too much RAM and then it starts to hit I/O. That's the only way we really let it fail on us. It's also free. I love free. Redis. Redis is new, but it actually survived the rest of everything else that blew up in our face. And we now keep it in our system permanently. If you don't know what Redis is like Memcache, but it's also got a few features on top of it. You have persistence, replication, and these really kind of cool data structures. You pay a little bit more in RAM cost, but you get a lot of convenience out of it. So the data structures include things like sets and lists and sorted sets, pub/sub, and blocking requests. It has persistence and replication, which is really nice, especially if you want to start using it for a little bit more than just straight cache. It's well known, well liked. Everybody loves it now. It's sort of everybody's talking about it. Everybody's heard of it at least, and most people have heard of it, and some people have even used it. It's got nice atomic operations, consistently good performance. The only problem with it is you have to know where its bounds are. But if you stay within those bounds, you're great. So basically, the only bound we ever found was you have to stay below 75% RAM if you use persistence. That's it, and then it's happy and it's blazing fast. It's also free. So what are the cons of that kind of setup? MySQL, Memcache, Redis. It doesn't do everything for you. Out of the box, they don't scale past one server. They don't have high availability out of the box, and they won't bring you a drink. So I'm not too excited about that. So when you start to grow, you really have to do some more. So you start wondering, I've got to bring more boxes in the system. They all have to talk to each other, and there's a lot of options on the table there. So we first classified them. You can think of this as a spectrum, and we named it like this. Clustering we named as really the pieces that are really fully automatic. They automatically distribute your data across your whole system. Data can move anytime, rebalances happen automatically, and nodes communicate with each other. And we labeled sharding as the exact opposite. Whereas that one's super smart, this one's super dumb and simple. And where you have to decide how to distribute the data. Data, once it's down in the pure sense, it does not move. Now, you can add a few layers on top of that and make it move, but in the pure sense of how we describe sharding, it does not move. It goes down, it's done. If you need to add more capacity, you will split a database into multiple databases, onto 2 new databases, and now you have more capacity. And nodes are not aware of each other. One node is over here, and one node's over here, and somebody else higher up talks down to them. So why is clustering a really great solution, and why did we buy into it? This includes things like Cassandra, Membase, HBase, and RIAC. And the great thing about these, when you see a white paper, you see a presentation about one of these, it's all glowing, it's all fantastic. It'll automatically scale your database. It's easy to set up. It spatially distributes all of your data. You don't have to do anything. You get high availability, you get load balancing, and there's no single point of failure. So why do you need an engineer? So we bought into it. This is fantastic. We set it up. It's free. Even groups like Cassandra even supply an image on EC2. You bring it up and you talk to it on the port. You're done. What could possibly go wrong? By the way, if you have any cats or kids, this is not a good thing to do in the house. Well, so what we hit was I think what other people have alluded to about clustering. It's still fairly young. It's only been around for a few years. It's not done. The community support is mixed because there's a lot of different new solutions and not many people know much about the details of it. It just hasn't been around long enough to get a really strong community base. There are a few engineers with working knowledge of it, so I rarely bring in somebody who knows RYAC or knows Cassandra, but everybody knows MySQL, everybody knows Mooncache. So that's a problem. It's also got a difficult and scary upgrade mechanism because you've got all these little nodes talking to each other. So one's going to be on 1.7.1, you've got to upgrade to 1.7.2, and they have these complicated things. Well, if you're on 1.7.0, you really need to go to 1.7.1 and then to 1.72, and it just gets really complicated. And yes, there is a single point of failure. I lied to you. It's a huge one, and we hit it hard. To illustrate that point, here's a typical cluster. We have 4 boxes. They're all talking to each other. They're all excited. Everything's great. One goes bad. One goes bad. There. So now you've got a route around it. You bring in a new box. You do the usual thing, and automatically the cluster points to it. Great. So there's no single point of failure. But there is. All of these run the same really complicated cluster management algorithm. And theoretically, just the theory of how to gossip between these is difficult, much less getting the implementation correct. All of these have to talk to each other. One has to say, hey, I've got too much data, you take it. And the other one has to say, okay, or maybe he says, no, I've got too much, and it gets complicated. It's way too complicated. It's too much code, and it nailed us. And the way it nailed us is it's the same complex code. It failed, and we had 4 major failure points across different clustering smart solutions that we use. Data rebalance breaks, so one day rebalance stops. What do? You call support, they're like, I don't know. That happened to us. The logs tend to be bad because it's still a young product, so the maintenance is still not a strong point. They almost try to push you into the support contracts in the hopes that that's the only way you'll be able to survive. Data corruption across all nodes. So you've got this one overarching algorithm that is really smart and doing its thing, and suddenly one day it decides to, I don't know, spray a bunch of bad bits, and it'll spread across the whole thing. And what do? You're toast. We actually had a CTO come up to us from one company and said, sorry, your data's gone. Like, okay, that's great. I'm not going to call you back. Improper balancing is common, where for some reason a lot of the data will be stuck on one server, and depending on how much control they have, which is not usually often because these things try to be fully automatic, you shouldn't have to touch it, you can't do anything. This data's all the way over here, this one box is hot, and the other boxes are sitting there happy on vacation. And sometimes you have to go all the way to support and say, how do I force this thing to be stupid and move the data over? Data authority failure also happened to us. You bring in a new box, it's at 80% done replicating off another box and says, hey, I'm the authority, you listen to me, and suddenly you lose 20% of your data. That happened to us, that was a fun 3 a.m. So our lesson learned, clustering is really scary. It's young. I mean, it eventually may take over, but it's currently young. It's not the proper solution right now, and it didn't work for us. So let's go with sharding. Why sharding? Well, first of all, you need sharding. If you're on one database, you need sharding so that you can have multiple databases to support your problem. You can split your databases to add more capacity. You can spatially distribute and collocate your data. It's just like clustering. You have high availability and load balancing, but the piece that really worked for us is that it's much simpler. You have to spend some engineering effort up front, but it's not that complicated when you get down to it. And what you end up with is a much more robust system that doesn't require much maintenance, and every piece of it is so simplistic that you don't have a massive, complicated, overarching oracle that can destroy your whole system at any time. You have literally one small page of code that decides where all the IDs go and where any data goes. So now you have to get into all the decisions about how you shard, and I'd also like to describe, we're also going to go into when do you shard, because that's also, that was a question that we got wrong. We waited too long, and to describe that, Josh is going to take over. Can you mute him? Who's got? Sorry.
So since you decided to go against clustering and choose sharding, the question is, like, when should you exactly shard? So this has been a question which was haunting us, like, should we take this step earlier, or like, should we just delay it and like go with like much better architecture, or like there might be a new database which would magically shard and like take us to the next level. So if you like shard early, you're like missing out the point of SQL where you cannot perform any simple ad hoc joins on your database and like build and ship features as fast you should be doing. But on the other side, if you like decide to shard late, just like we did, you have this huge, humongous pile of data sitting in your old database, and then you have these new shiny shards, and like you got to make sure that your application splits your writes to both these infrastructures, which is pretty complicated. Like, I mean, like as a matter of fact, like performing writes is way simpler, but keeping the two database in sync is like way tough. And like there's this question of like, we had where a lot of issues where like users change their password, but the new password hasn't been migrated to the shards, and like we had like code where like, okay, if this user exists in shard, go respect the shard data. If it doesn't exist, go to the old database, read from the old database. And like there were like lots of problems. So like when you like decide to shard, just make sure like you are in this migration phase for as less amount of time as possible. So like, before you even attempt sharding, like make sure your site design is solid, just lock down your product features and like do a feature freeze. Like you're not gonna build any new features for the next couple of months, and like make sure like the current schema is the one you want to go through into the shards, because like you're like, when you apply migrations into the shard, you're just like multiplexing your effort. You gotta run your migrations on all the shards, and your application code has to be tolerant to these migrations. And so like, the first step to sharding is like, make sure there are like no joins in your code base, almost like 0 joins. And then remove all the complex queries, which includes like joins, add as much cache as possible. Just don't go to the DB for like a while. Just take the hit in your, take the hit in the servers, like just add more cache and just make sure you're not going to the DB much. And then before you attempt the final sharding, just functionally shard as much as possible. This is like the cheap sharding, where you like take your huge table and move it to its own database. So in case of Pinterest, it was like a pins table which was growing a lot, and people were repinning a lot. So we just moved our huge table to its own database and just rewrote the application code to talk to the database. And we got away for a couple of months to deal with it. And still you're growing with a lot of volume, query volume, then it's time you should think about serious sharding. So this is how like Pinterest transition looked like when we were sharding. We had a single database, and we had like proper normalized data with all the relations between users, votes, pins, likes, comments. And then like as the query volume started to mount up, we slowly started to denormalize, delete the foreign keys, add proper indexes, apply the explain statements, and make sure you're hitting index all the time. And then even then the query volume went up with the traffic, add read slaves, add more cache. And then the cheap sharding, like move your largest table to its own database, and then get away for a couple of months. And then you finally bite the bullet, like you really partition and spray your data across all new shards. A couple of things to watch out when you shard is you have no question of joins. You got to replicate, add redundancy to your data and write your tables such that your queries are very simple static queries rather than any joins. And another feature we lost was like we couldn't do transactions anymore. Like when we had to write to 3-4 tables, like we had to go to a different shard, complete the write, go to a different shard, complete the write. So there's like no question of transactions. But I think it was okay in our sense, in our case, because like we're not a bank and like we don't have like serious conflicts of issues there. And when you have these unique constraints, like you have to maintain a user table with username and email as unique, you can't pretty much apply sharding solution out of the box. Like you got to have a huge database with single table where you write to the table, and once the write succeeds, that means the email or username was unique, and then you proceed to the shards to complete your writes. So when you have this simple report running as cron jobs, like you got to rewrite these to run on all the shards, aggregate the data, and then email the reports to your dev teams and all. So like those were the couple of things we had to watch out for. So how we sharded. So we took a very close look at how all the other people like sharded. Like we took a close look at Twitter's architecture, and then Flickr's ticketing service architecture, and like we took a close look around the Cassandra's ring-like structure, where when you add a node, you just repartition the data across the adjacent nodes. And like one lesson we learned without even implementing was like the less data you move across the shards, the more stable you are and the less work you have to do. So like with that as our important motto, we just started to shard. We just pre-sharded for the next foreseeable feature for Pinterest. So like we just created a lot of databases on single machine, and we just split the databases when we are under a huge load of the database. So like initially we started with 8 servers and started with 4,096 shards, and we had 512 databases on each machine. And as we started to grow, we just throw cache, and then even then the query volume bounds up, then we move half of the databases to its own shard, and then make the application configuration like, okay, the new shards are in this host and the old shards are in this host. And that's how we just scale out of the box within like minutes. And high availability, like we just run all our shards in multi-master replication mode, and upon like failures in Amazon, which are pretty imminent, we just flip the switch in our application configuration to move a bunch of shards into read-only mode for 1 or 2 minutes and let the replication catch up. And then we flip the read-only switch, and then the writes again kicking back into the new mode. And then we take a slave backup of the new master again, and then again it's all the same story. And all the shards are pretty symmetric, like we have equal distribution of databases. Although we can go like hybrid structure where like if there are like a couple of celebrities on like each shard, we can just like pull that shard out and put it on its own machine and like deal with the scaling. So what happens when you have an increased load on the database? We just track down and profile our app right from the user's browser to our network, and then like measure the latency, like what's happening. Was there any bad code that's being pushed over the last couple of weeks? We go through our Ganglia graphs, and then like we come to the database and like see profile with MapKit, and then see what kind of queries have been creeping up, and then like, okay, I think these are the right sort of queries. We just have a huge query volume, and the traffic has been steadily increasing. Then we like decide to split the shard, where we just like move half of the databases to the new host and push the new configuration file to our application service to like, okay, these shards are in this physical machine while these shards are in this new physical machine. It's pretty easy to do, like we just do this in like 12 minutes. So this is our ID structure. Like, so every ID in Pinterest architecture is like a 64-bit ID, where we dedicate a bunch of bits for the shard ID and a couple of bits for the object type and another couple of bits for the local ID inside the table. So instead of building a routing table and maintaining it and adding redundancy and replication and high availability for that index-based database, we just chose like what if you just have this routing built into the ID? We could just build services agnostic of language. We can just write this in Java, Python, and like 6 lines of code. Just like do the bit manipulation, get the shard ID, what is the table I have to go to, and get the local ID, and bam, that's where your data is. So pretty much like when you ask for a pin, we just like do a cheap validation, like, okay, is it exactly pin that you're looking for? And if the object type doesn't match, you're like, okay, this is something wrong we're doing. So like we built a REST layer on top of our MySQL, so we pretty much use MySQL as a storage engine, and that REST layer just peaks all the sharded infrastructures calls. You just make a REST call and it would just go to the shard and get all your data back and return it to you. So why not an ID service? Like we saw like Twitter build this Snowflake which generates 64-bit IDs. Even so, like it's pretty handy to have to generate ID even before you write to the database, because you can just spawn a different in parallel all your tasks. Like you write to the database, deliver it to all your followers, and you can do a lot of cool things. But we just felt like it's another piece of infrastructure you got to maintain. Just what if the ideal service just goes down? Like the master and the slave, both of them, and what if it goes down? Even though if your shards are up, you just can't function because we don't know where your data exactly exists. And we don't want to do an extra lookup just to know where our data is. So that's the reason why we went with building a routing table right inside your ID structure. So here's how our Python code looks like. We have this huge dictionary to map, like, okay, the shards 1 to 512 exist in this host shard DB001A, and 513 to 1024 exist in 002B. And like when there is a failure, we just flip the multi-master replication, then the shard DB002A becomes the master from now on. Let's say we have to pick a user who exists in DB1025. We go to the lookup table and find out like the data exists in shard DB003A, go to the table, select the database 01025, go to the users table, pull the serialized data out of the user, and there's your data. I want to talk a little bit about the ID structure. So we basically sharded on the user, and the reason was we had a huge opportunity where we could collocate all of the user data on one shard. Say you're rendering my user profile, you just don't have to go through all your 4096 shards to get the data. All user's data is collocated on his shard. So like if you're rendering a profile, you just like connect to one shard, get the user, get his boats, get his pins, just render the page, and like done. And most of these queries are even like cached, so you just don't have to spend time going to MySQL most of the time. And the local IDs are assigned by auto increment in MySQL, and we all know like MySQL auto increment just works out of the box. It's just like the most robust solution there. It just works perfectly, so we don't want to like build any auto increment system ourselves. So instead of opening all the 65,000 shards initially, we just chose to open 4,096 shards initially. So that like when we feel like okay, there's going to be enough users on these shards and we're going to have a lot of pins for the next 10 years, we just shut down this range and open another range like 4,096 to maybe like 10,000, and we're going to push the new users into that range, and all the data will be collocated into that new range. And this way we can just go through 65,536. We have some reserved bits in the 64 bits, so like we can just like scale for like a lot of years. So basically every data inside our database falls into two categories. Either it's an object or it's a mapping table. So all our objects tables have been designed after FriendFeed's MySQL post, like by Greg Taylor. Like every object is almost in a local ID, which is the auto increment, and just a MySQL blob. And we just store serialized JSON data or serialized thrift data. Like we just started to muck with thrift. And the others part is like the mapping table. Let's say like you want to find all the boats that belong to Yash. So like you just go to the table called user has boats. You just query on the user ID, you get the boat IDs. Then you go to the boat table and just get all the boat data out. And it's like you just decompose your join, and like each query has a cache before it. So like effectively you'll just hit a mem cache. And every mapping table has a timestamp just to like have the ordering, like when did you create a boat and what is the order you created the boats and all that. And we chose a careful naming schema, so all the mapping tables are like noun, verb, noun, just to be descriptive, like user follows boat, user likes pin, and all the objects are just nouns, like users, likes, comments. And almost like 60% of our queries are simple primary key lookups, like give me this user, like give me these 10 user IDs, give me these 20 users, or like give me the boat IDs that belong to this user. There's always a primary key on the mapping table on both the columns, so it's like 60% of our queries are like super simple primary key lookups. And the most important thing of our sharding is the data never moves from any shard. Once the data is in that shard, it's going to be in that shard forever. We just move the shard to a different host, but we never move the data from a shard to another shard. That was one of the reasons why we really like the current approach, is like you don't have to move data from one shard to another and like update some mappings, which is like a lot of hassle. But you might get data symmetry across your shards, but this is just out of the box, super scalable solution. And all tables exist on all shards. There are no like special shards. it's just super symmetrical solution. And one approach is like we do not have to run any schema changes. Let's say you want to add an attribute to a user like location, you just go and start adding location to the blob, and you can version your blobs like, okay, the last version was this, and when the next time you read, you can repair the blob and write it back, which is like super cool. And like if you want an index, just create a new table and start writing to that table. So like if you want to get all the users in Santa Clara, you just add a new index table called location_users and start writing the location and the user IDs, and we just create the table. And tomorrow you want to drop that index table, just drop it, and it's just a matter of seconds. And here's the some pseudocode how we create a pin. So like we take the board ID to which that pin belongs and pass the pin data. We just decompose the board ID and get the shard ID and the local ID of the board. But then we issue a write to our REST layer where like, okay, complete this write to this shard of this object type, and here's your data. And it just returns the local ID in the table, and then we compose the complete global ID and just return the pin. It's like as simple as that. Here's how we render our user profile. So like, that's the user profile page on Pinterest. So you basically get the username from the URL, do the username to user ID lookup, break the user ID, get the local ID, go to the table, get the user object, go to the user has boards table, get the board IDs, go to the boards table, get the boards, go to the board has pins table, get the pins, go to the pins table, get the pins. So like it looks like we're running a lot of queries, but all of these are like simple memcache hits, and like we do not have redundant data in memcache. It's like either an ID to ID or an ID to an object inside memcache. So we just have like pretty much down to metal. Scripting. This is another stage in your sharding that it's constantly underestimated, but I think this is like the most important and painful part of your sharding, where you write this application code to split your writes to the new shards into the old infrastructure, but you have like a few days to move all your old data from your old infrastructure to the new shiny shards. We had a huge problem dealing this. Like we wrote a couple of mistakes in the scripts, then we had to like drop the data. You just had to spend enough time for capacity planning this, and like you just need enough time to like move your data from your old database. And like we just built a scripting farm where we just like put more Amazon boxes and just add these workers to our queue and just put all the old IDs and then into a list, and then we pop each ID from the list, go get all his associated data right to the shards, and then just keep doing rinse and repeat the same step. We used an open source project called Pyrus, which is on GitHub, which is effectively a clone of GitHub's Rescue, which is based on Redis list. Fairly simple. It was like awesome, and we just adopted it as our task processor in our infrastructure. Here are some future problems we are like trying to hit. Like we have these hundreds of app servers connecting to pretty much every shard and like all the memcache boxes, and like we're blowing up connections on our memcache boxes. We started memcache daemons with like 4,000 connections, and like we hit it pretty fast. We had to kill the daemon again, like start with 12,000 connections, and like constantly when we're having more traffic and we're booting more app servers to handle the load, we're just blowing up the connections, and we can't keep doing this forever. So like we're looking into service-oriented architecture where you just have like a search service, a follower service, and like pretty much like the bigger chunk of your code, just like move it into a service and like have teams dedicated to the service and just make it faster. And it's just more easier to manage and just more easier to scale as well. Like you just measure the latencies on each service, and then you can like scale it much better rather than having like a huge monolithic code base. A couple of interesting tidbits we learned while we were sharding was like, read slaves are great, but they won't just take you forever. Like we added one or two read slaves. It was great, it was working, and like as we saw more traffic, we just threw read slaves, and we were incurring that IO cost on all the slaves. We had like 5-6 slaves at one point, and like we realized like this is not working. Like the master is under huge load, and like the master has to distribute all its data to the slaves. There's this replication lags, and like somebody pins and like they go to the page and it's a 404 because like the data hasn't been transferred to the slaves. So like it's just a temporary measure. Like if you think you need more than 3 slaves, you just have to rethink what you're exactly doing and what you're trying to achieve. And another feature we learned is like when you're building feeds, Memcache and Redis are your like best friends. Like the ability to append, perform atomic appends on a list is just valuable. It's like that's how like Twitter and like Pinterest feeds are like powered. It's like completely Redis list. Like you just push these bits of data into the list and they just appear almost real time. And you can do this in a much optimal way. Like Redis supports transactions. You just ship a huge text file like, okay, append this new ID to like this 5,000 lists, and like it's just written in like 20 milliseconds. And one thing we learned is like if you prioritize your background task, you just get a lot of efficiency. Initially, we had a bunch of workers dedicated to repin this, resize this new pins, and we had a bunch of workers dedicated to like push these pins to all the followers' home feeds. Instead of doing this, we just started prioritizing the tasks, and so we had like this prioritizing queue where 10 being like the top priority and 1 being the low. So like when we push all the workers first perform a pop on the highest priority. If they get a job, they just finish it, and they keep falling back to the lower priorities. So that way we just had one huge cluster, and we're running these scripting jobs at like priority 1, like okay, move all this whole data of these users to this new sharded infrastructure. And like as the new pins coming, we were just serving the requests, and when the traffic was low, all our workers were spending all their time like scripting the data from your old to new infrastructure. We just wrote a custom ORM tailored to our sharding. Like you just ask, like give me this user, it would just perform a Memcache lookup, go to our REST layer, fetch the data right to the cache, give it back to you, and it would just like does some cool stuff like, you know, like put an increment into the stats tree, like is it a cache hit, is it a database hit, and like it's pretty much like worth time investigating into building an ORM and have all these cool features built into your ORM. Lessons we learned, at least for me, was like working with Pinterest is awesome. Like you just get to work on this cool stuff, and pretty much you should just reaches millions of people in like a couple of seconds, and we just deploy hundreds of times every day. And just like every other company, we are hiring. If you're interested, like share or like write us, email to us. And with that, I'll just leave it to questions. Sure.
Do you do any analytics on the behavior of what happens?
Like what? Sorry.
Like,
we just hired our data team, like new guys like Mohammed and Dimitri, like who just set up this huge EMR cluster, and we are using Flume to log all our data into this cluster, and we are running Hive queries. It's been like fantastic, but we're still like learning to log. We're looking into Thrift and like JSON, and like we're still in like pretty early, but we are definitely extracting some data from all the data we collect.
are you the only 2 DBAs?
We're like the early users who worked on the sharding part, but right now we have
12 engineers. We do a little of everything at this company. Any fire, we send some guys on it. So we don't really have a person who's a DBA.
Well, good
We're
job.
all DBAs.
I was just say, are you hiring? Because everyone's hiring.
Oh, we're hired. Yeah, it's a one backslide.
There you go. Exactly.
Hiring.
That's what you
Real quick, I just want to also, can everybody hear me? I don't know. I wanted to acknowledge real quick, this is Ryan Probosco. He was also heavily instrumental in designing everything that we built, but he couldn't be here today. More questions?
How do you, this is nothing to do with databases, but I'm interested. How do you deal with, you know, that age-old problem of, what do they call it, bandwidth stealing or something? Like if you use a picture from something else, do you actually copy the picture?
Yeah, we copy the image into our CDN and we create like a couple of thumbnails of different sizes, and we actually credit the end to their source.
Right. Well, that helps, but you're also not stealing the bandwidth with using the picture.
No, we
so
just
that helps.
completely
That's
copy
the
the
big thing,
picture.
yeah. Okay.
In your active master education, are they both active or one has a...
Only one is active. Although we can just make our REST layer point to the other active, we were like, you know what's the point? Like the single shard is able to handle all our traffic, and pretty much it's a PK lookup. So we could, at any point of time, only one guy is the master.
And then for a given member, you have all these data pins, all board, everything is in one shard?
That's almost completely true. We do have a few things like our system allows us to put it anywhere, so we have collaborative boards. So I can actually put a pen on a collaborative board, which may be on a different shard. But because our mapping table has full IDs to full IDs, I can map a user ID to any boards anywhere. Trying to keep stuff collocated is really more of an optimization, but it's not a requirement at all. And in fact, we do have mappings that point to different shards.
Just
So
to
mapping is global ID to global ID.
That's right.
Yes. Just to explain a bit more, like let's say I have a board and I invite you as a collaborator, and let's say I have like a TechBooks board which I have on Pinterest. So like if I invite you as a collaborator and when you pin something, the pin goes to my shard because I own the board. But you have this mapping table where like user has these pins, but only the mapping goes to your shard, but the data exists on my shard, basically. Yeah.
Do you guys use Memcache from Redis, or is it just for the?
We just use Memcache as like an object cache, which is like user ID to the object, basically JSON structure of object of thrift serialized. We use Redis only for like lists and sets.
But actually, one cool thing we do with Memcache is it has this append notion, which not many people use. And if you use a streaming list for your value, you can actually append atomically to that Memcache list, and now you've got a basic feed inside Memcache. The cool part about append is that if the key doesn't exist, it doesn't actually do anything. So what you can do is if you have a user to pins view, you can bring in a cache for that. It's this feed cache. You bring in a new pin, you put it on the list, and the list doesn't exist, it doesn't get populated. So then if the key gets evicted or you bring in a new cache, you don't have to worry about having partial lists and having to script it. So then the next time the person views their list, then we'll populate that Memcache list.
So basically we built a list on top of Memcache because Memcache has a prepend and append. But we had to do some stuff like you add a +2 and you remove +2, you can't remove it because there's no remove notion in Memcache. So you add a -2 and again +3, -3. But there were like these bugs where like if the cache was fragmented, it was on a bunch of keys, you got to start parsing from the back of the key because if there's a -2 and a +2 at the end, we would just like remove but add it at the later, which is like a wrong. So we just like thought like, okay, Redis is just giving this out of the box. Like why have this and deal all this complexity? So we just moved all our lists into Redis cache and we just use Redis as an LRU and it just works fantastic.
One of the previous slides, so I used MongoDB. Now, was there a specific reason for replacing with Memcache or
We don't have any production serving traffic on Mongo. It was like an analytics tool, like because like every day, like, oh, I want this new analytic column, like I want this aggregated to the last 30 days, last 45 days, 30% of our users, and we perform these tests in our A/B experimentation and all that. So we can't keep running like schema migrations on MySQL. So that was the reason we chose Mongo. We had a lot of other data in Mongo, but once we went through the catastrophical route, we just dealt like all production data only sticks in MySQL, and they allow you Memcache or Redis, and nothing else. Sure.
you use Amazon EC2 for the compute, you have your own databases and your own data centers? Like,
No, we run all of our MySQL infrastructure on Amazon.
Everything's on Amazon.
Everything is on
It's
Well,
not RDS, we just host our MySQL boxes ourselves.
Images are not. Those are served by S3 and Akamai.
Just to be clear, we don't use EBS, we just write to the local ephemeral drives. We use the 15 gig instance, which has 4 drives. We rate all the 4 drives for the data, and we have multi-master in different availability zones. And we snapshot the slave shard every 24-hour interval and upload it to S3.
Thanks for coming.
Yeah, any questions?